Hey guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So in this specific discussion, we're going to look at a second part of the representation of internal energy using the partition function. And of course, this is going to be a follow-up discussion from the first one where we had looked at the various differential laws which are going to be applicable. So in this case, I had mentioned the concept of this specific internal energy, and we had given it using this specific formula of the summation of this specific element from the initial state, whereby we said that basically the partition function represents all the thermally accessible energy levels at a particular temperature. And we had said, therefore, that we're going to give this one as a summation of this initial energy, and then we are going to have this exponential form, which basically I elaborated on. But I'm going to just give a short description of what's basically entailed. So this is going to be the general representation of the internal energy of our system. And in this case, we're going to look for some ways in which we can represent this one in terms of Q. Now, this basically is going to involve some of the laws which we have looked at, especially on the differential calculus. And this basically is going to be entailing the concept of rearrangement as we have been doing in some of our algebraic representation. So in this case, I'm just going to remind us of a few laws which we have looked at, which we said basically if we have a function which has been raised to a power, we can find the derivative of this particular function by finding this specific power given as a coefficient, and then we're going to have this specific number and the power minus 1 given as such. So in case we come across this one, we're going to remember that basically that is what it's going to represent. And this is going to be applied across the numbers for the positive and negative. So in this case, there are some unique cases whereby we're going to come across natural logarithms, especially when we're going to encounter differentiation, especially on the concept of this specific reciprocal. But of essence for us to remember is this specific law. And then I'm going to remind us of one of the exponential laws which we had looked at, whereby if we have e raised to power x, the derivative of this specific number, then therefore is going to be given in terms of dx. So we're going to consider this specific number given as this specific coefficient, which was a power, and then we're going to have e raised to power x given as such. Now there are some unique cases which maybe we might come across, which basically might consist of a range of numbers for the exponent. For instance, if we have e raised to power ux, now in this case we're going to have for this specific derivative given in a different version, whereby we're going to have this one given in terms ofeux times du over dx, which means we're going to find a derivative of this exponential element in some way. And of course, this is going to be one of the ways in which we are going to deal with this natural logarithm or our natural number e that we are going to use in this case. Now, suppose we have perhaps a constant which is accompanying this specific power, whereby we have a cx, whereby c is a numerical constant. In that specific case, I can perhaps give a specific example for this. We're going to have this one represented in terms of this constant ECX given as such. Now, an example of this which I can give just a rough for the sake of clarity. So we're going to have, in case we have e raised to power 3x. Now, the 3 in this particular case that I'm giving is going to represent our c. Therefore, we're going to have this unique case for the derivative of such a kind of functions, whereby we're going to have it given as 3. This particular power is going to be given as the only exponent, and we're going to assume this element of x. And then lastly, I'm going to have this one. So in case we have a number like 1 over t, now this basically can be represented in terms of a power over t negative 1 given as such. So if we consider this one to be an element like x in this particular case, then therefore we're going to have this one in terms of a representation given as t negative 1. Now we're going to have this specific coefficient of negative 1 minus 1, and then this particular m in terms of negative 1 is going to form our coefficient, which is a negative 1 even in that specific case. And therefore this is going to be in terms of negative 1 t minus 2. But remember, this one basically from this specific law is going to imply an inverse or a reciprocal, and then therefore this one is going to be -1 over the square of t given as such. So whenever we're going to come across differentiation that are involving a quantity with respect to temperature, for instance, we are going to have this specific section for representation of this notation, which we are going to use in our case for various representations over the partition function. And therefore, we're going to consider this specific law in case we come across that one, and that is going to be more elaborate for us. So in any case, if I mention one of the laws that I've just given in summary form, then therefore it's going to be easier for us to remember that one. So definitely, then therefore, if we are going to represent this internal energy using that specific equation, we can rewrite this specific equation in terms of Q, which is a partition function, by first finding the derivative of this specific function with respect to temperature. Now, the specific laws which I've mentioned and therefore are going to be applicable in this case, but the derivative of this expression with respect to temperature is given in terms of dq dt, and this is going to be given as the summation of I ui over k bt, and then we're going to have this one as the exponent of this specific. Of course, we're going to have this one just retaining its value as such. So I'm going to explain on this, particularly concerning the laws that I've just discussed before this. So if we have this specific exponent in terms of x, we are going to assume that, so this is going to be a square, basically from the laws which I've discussed about the 1 over t, given in this specific case for 1 t raised to -1 for a derivative with respect to temperature. So in this case, if we have this specific exponent, I'd say that we can find a derivative for this exponent in terms of x, ex as such. So if we consider this specific component to be this one here, then therefore we're going to have it being given as a coefficient of the exponent. Therefore, if we look at this specific expression in terms of the second law which are defined for this, therefore we are going to consider this one in terms of eux times du over dx. So consider in this case the derivative with respect to temperature, which we have given in this case, which is going to, of course, result in us having to find the derivative of this specific u, which we have represented in terms of this specific exponent for ux given as such. Now, I've said that for these types of expressions, then therefore we're going to find the derivative of this specific t given as such, or this part of the exponent with respect to temperature, which is going to result to kBt squared as per this specific law which I have given. So therefore, I'm going to assume that this transition for this expression of writing the first one in terms of the first derivative with respect to temperature, then therefore is going to become more elaborate for us. So from this one, we can do a rearrangement by first, perhaps I'm going to take this part of the equation and multiply it on both sides, and this is going to be the numerator, or rather the denominator of this ui given as such. And in this case, of course, we might ask ourselves where the negative sign disappeared to, and this is going to be due to this specific factor. I said that if you consider this one to be x, it's going to form a numerical coefficient given as such, and of course a -2, which is -1 over t squared given as such. So this element of a negative and a negative are going to make this one positive. So in that case, we're going to have this one by doing a rearrangement, whereby we are going to multiply both sides by k subscript b, the square, and then k. So this is just a transition that is going to make some rearrangement, but it's going just to keep the value of this specific expression. So therefore, this specific component is going to cancel out with this one, and then we're going to do a subsequent rearrangement of a division by q. So the first rearrangement we do is multiplication on both sides of this equation. I'm just doing this because of space. Multiplication on both sides of this equation by kb, the square of t, and then we're going to do a subsequent division by q, and then we're also going to do this one by q respective. So I presume that this is going to be 1 over q given as such. So therefore, we are going to have a resulting equation given in terms of a kbt times 1 over q, which is an element, of course, of the denominator of this, and then times the q over the dt, equivalent to the summation over I, and this energy given as such, and then the exponent over negative ui all over kbt, and then of course this is going to be times, or rather times 1 over q in that specific order. So this is going to be a transition of multiplying both sides by this specific denominator, and then the subsequent step is to divide by q on both sides, and then we're going to have this specific equation given in this specific form. Now I'm going to transition this second part of the equation on my right by having this perhaps second part of the expression given in terms of a rearrangement over negative ui all over k bt. So this is going to be given as such. So this is the exponent, and then I'm going to have this one all over q. So this is just basically the same as this. This particular exponent has been multiplied times 1 over q. So I'm going to have this one given as q. But from our previous definition, we had looked at the concept of the partition function using this specific second aspect of the expression. Therefore, we are going to have this one given in terms of a q, which is a partition function. So we defined our partition function using this specific section of the equation. Therefore, we can have this partition function cancelled out, and in this particular part, we are going to remain with this specific section equivalent to this section on my right. And therefore, we can proceed and have this equation given in terms of, so the summation of all these elements from the initial one of this specific energy is going to give us the total internal energy, which basically on this side I'm going to have it represented as q. Therefore, on this side I'm going to have this element of kbt square of that. 1 over q, as I said, represents the natural logarithm. So this is 1 over q, the q with respect to temperature. This is going to represent the natural logarithm of this specific element. Therefore, we're going to have this specific section represented in terms of the partial derivative of natural logarithm of q with respect to temperature. And in case, of course, we remember this specific, of course, section of this partial derivative for natural logarithm with respect to temperature. This basically is going to be a transition that is going to be with respect to constant volume from our previous discussion we had on the summary of thermodynamic variables. So I'm going to have this one given as subscript v, and this is going to be our equation that we're going to use in representing the internal energy of a system with respect to the partition function, which I've already been stating. So in this case, we're going to consider this specific partition function, and of course we're going to see that we can do a measure of this particular partition function from the grounded state, which basically is absolute zero temperature, and therefore we're going to see that the nature of this specific internal energy in the partition function is going to depend on the temperature, and therefore we can do a consideration from the grounded state of this specific temperature for u naught, and the difference between that one is going to dictate the occupation of various energy levels, of course, with the temperature. Therefore, it's going to imply that basically the upper energy levels of this specific system, or the rate at which this internal energy is going to be occupying this specific, of course, higher levels is going to depend on the temperature. And of course, that is going to be more elaborate, perhaps, if we're going to do some elaborate or particular examples. But basically, as I have just given, but done it in a compacted way, I hope that we're going to follow this in terms of a partition function. So catch us in our next video as we're going to look at another aspect of this thermodynamic variable, and we're going to see how we can represent it as well in terms of the partition function. So that is it for now, guys. Bye, God bless you. Catch us in our next video.